For a polynomial function f of x, solutions to f of x equals 0 are called zeros of f of x. So this is how we can find zeros of our polynomial function. Here's an example with a quadratic polynomial function. So solutions to f of x equals 0, so we're replacing f of x equals 0. Right? So those solutions can be found, in this case, by factoring. And then the zero factor property says either x plus 3 equals 0 or x plus 4 equals 0. And that leads us to negative 3 and negative 4. Those are the solutions when we let f of x equal 0. They're called zeros of our function. So definitely we have this relationship between factors of the polynomial function and zeros of the polynomial function. I also want to consider the graph quickly to see another relationship we have here. So here is our polynomial function. I could find the x-intercepts by letting y equal 0. Remember, f of x is just our fancy name here for y. And so if we let y equal 0, we find the x-intercepts, right? And we've already done that work. The x-intercepts for this function are negative 3 and negative 4. We could also easily find the y-intercept. If we let x equal 0, then we'll have 0 plus 0 plus 12. So our y-intercept is 0, 12. But I want to come back to the relationship here between the zeros of this function and the fact that if they are real, then they are considered our x-intercepts. So we have three important aspects of our zeros here. So zeros come from factors of f of x, right? And if they are real, then they are x-intercepts on the graph of f of x. Now let's see. So we knew we had our x-intercepts, we had our y-intercept. That's enough to tell us that this parabola is opening upward. Also notice that the leading coefficient here was a positive 1. Right? So that it was positive means our parabola opened upward, and just 1 means we didn't have a vertical stretch or a vertical shrink. So let's consider another situation where we do have a vertical stretch or shrink. So here is another quadratic polynomial function, negative 3 times the quantity x minus 4 squared plus 12. Now this is in our form where we can tell what the vertex is very easily by knowing how far our graph has shifted left or right and how far our graph has shifted up and down. So looking right here, this tells me we went right 4. This tells me this graph went up 12, which places the vertex at 4, 12. So I have a sketch of that graph here. Here's our vertex at 4, 12. Now, the negative 3 multiplying our function is going to change the direction. It's going to change the reflected about the x-axis. So this parabola we see is opening downward. And then the fact that this isn't just 1, that this is 3, is going to make what we call a vertical stretch. So that makes our parabola narrower than it would have been if this had just been negative 1. So in this form, we can find the vertex. We can also find the x-intercepts. That's just where we let y equal 0. Remember, this is also the same thing as finding the zeros of this function. So if I replace f of x with 0, I'll have 0 equals this expression here, and then we can solve. We can subtract 12 from both sides and have negative 12 is negative 3 times x minus 4 squared. I need to isolate the x minus 4 squared, so we're going to divide both sides by negative 3, and now we have 4 equals x minus 4 squared. We're ready to use the square root property. I kind of usually do this way, left to right. So if we flip our equation around here, then the square root property says x minus 4 equals plus n minus the square root of 4. Okay? So x minus 4 equals plus n minus 2. when we add 4 to both sides, we'll have x equals 4 plus 2, and then also x equals 4 minus 2, right? So that's that 4 plus 2 and 4 minus 2. So we have x equals 6 and x equals 2. These are real numbers. They are real number zeros of the function. On our graph, they are x-intercepts. So we have the x-intercept of 2, 0, and the x-intercept of 6, 0. So again, tying together the idea of zeros of the function, if they're real, are x-intercepts. And I want you to notice also here the fact that we had this coefficient, right? This negative coefficient affected that we were reflected downward and made our graph narrower. Now, the next step that we're going to do is use information to write the equation of a polynomial function. So let's say we're given these directions. We are to find a polynomial of degree 3 with real coefficients and zeros of -3, -1, and 4, for which f of -2 is 30. So let's worry first about the relationship between the zeros of the function and factors. Right? We saw in our earlier examples that these zeros come right from setting up the zero factor property. So we're going to use these values to plug in, and that's going to give us our factors here. Okay. Then I use the a value here to show that we can have that constant multiplier. We just saw in the earlier example that a -3 here caused our graph to reflect downward and made it narrower. Okay. So we don't know what that coefficient is in this mystery polynomial we're trying to find. This information is going to help us do that. So this part right here is what we are going to use to find the a value. But first off, let's see if we can work on the rest of our polynomial function. So f of x is going to equal that mystery coefficient a. And then let's work with our zeros here. If -3 is a 0, then x plus 3 is a factor. Right? Because if we set this equal to 0, the solution is -3. Or you could plug in -3 here to our x minus k form and see we get x plus 3. If -1 is a 0, the factor that's related to is x plus 1. And if 4 is a 0, the factor that is related to is x minus 4. Right, so if we turn this around and we wanted to, if we had these factors and we wanted to find the zeros, we would just set each factor equal to 0. Now I'm going to go ahead and simplify this before we worry about that a value. So let's do some distribution here. If I distribute for these two binomials, we'll have an x squared plus 1x plus 3x plus 3. Right? And that still needs to multiply x minus 4. We'll combine some like terms here. That's x squared plus 4x plus 3. And that needs to multiply the x minus 4. And we can keep distributing. So the x squared has to multiply both of these. That's going to give us x cubed minus 4x squared. The plus 4x has to multiply both of these. So that's going to give us plus 4x squared minus 16x. And then the 3 needs to multiply both of these. So that's going to give us plus 3x minus 12. And when I combine all of those like terms, remember all of this is still being multiplied by that mystery a. We have a times x cubed. Let's see, we have 0 x squareds, but we're going to have negative 13x and then minus 12. So just working with the zeros that we're given, we can reach this form of our polynomial. We know where it crosses the x-axis, right, at all these real 0 values. But without this information, we don't know if it's been reflected across the x-axis or if it's had a vertical stretch or shrink. Okay. Now we're going to bring this in to figure that part out, to see what this a value is. Okay. So this is telling us when x is negative 2, then y is 30. All right, so let's write that out. When x is negative 2, y equals 30. Well, if we come to our function here, this is y, and we're going to plug in negative 2 here. So negative 2 cubed minus 13 times negative 2 minus 12. And this is going to allow us to find that mystery value a. So 30 equals a times negative 8 plus 26 minus 12. Negative 8 plus 26 minus 12 gives us 6. So we have 30 equals a times 6, and we can divide both sides by 6 to reach a equals 5. So we have put all of our puzzle pieces together here. Now we are trying to find the polynomial, degree 3, yep, we have degree 3, with these zeros that fits this requirement. Right? So this led us to the fact that a is 5. So here's our polynomial. Our polynomial f of x equals 5 times x cubed minus 13x minus 12. If we're asked to simplify this, then we'll do the distribution 5x cubed minus 65x minus 60. So here is how we can use given information about zeros and our function to write the polynomial function. And we're going to try one more. Because I mentioned when we were looking at how the zeros of the polynomial function were x-intercepts, I mentioned that that only happens when those are real zeros. It is definitely possible, we've seen, to have zeros that are not real numbers. So we are going to do a similar problem here. We're going to find the polynomial function f of x of least degree, having only real coefficients and zeros 3 with multiplicity 2 and 3i. So this problem is giving us zeros. Our zeros here are 3 and 3i, just like our last one gave us zeros. It gives us some information that this 0 of 3 has multiplicity 2, so that means we're going to have 2 factors from this. Notice that this one does not tell us any specific point. So last time we had f of negative 2 equaled 30, right? So we don't have that information here. That lets us off the hook for finding the value of a. Right? So let's come along and see if we can set up our factors. So our f of x, I'm going to put a here just so we're in that habit, is going to be a times and then our factors. So if we have a 0 of 3, that means we have a factor of x minus 3. Now when it says this 0 of 3 has multiplicity 2, that means there are 2 factors of x minus 3. And then we have another 0 of 3i, so we'd have x minus 3i. And now we need another important bit here. If 3i is a 0, then its conjugate, negative 3i, is also a 0. It's just a fact that these complex zeros, right, whether they're pure imaginary or non-real complex, are always going to come in pairs. So very often you'll have a problem that only tells you one of those complex zeros. It's our job to recognize they have to come in pairs. These come in pairs because the I, remember, that comes from if we had the square root of a negative. And whenever we take the square root, we're always doing plus and minus the square root. So if positive 3i is a 0, then in the process of the square root property, negative 3i is also. Okay? So here is my positive 3i being a 0. here is the negative 3i being a 0. Now I emphasize that fact that our form here is x minus k, where k is the 0. But of course, this is just x plus 3i. So if we have a factor of x minus 3i, we must also have a factor of x plus 3i. Now again, this problem did not give me information about a specific point on the graph, so we can just assume that our a value is 1. But let's simplify these factors. Okay, we're going to do all of this distribution. Let's go ahead and do it step by step. Let's multiply these two. So we're going to distribute x times x times negative 3 times x, and negative 3 times negative 3. And that's going to give us x squared minus 6x plus 9. And let's also then go ahead and distribute our complex conjugates here. I'm going to rewrite this, just so we don't have to worry about that double negative. So we have our x minus 3i. Remember, this is just x plus 3i. And let's go ahead and do this distribution. So x times x times positive 3i, then negative 3i times x, and negative 3i times positive 3i, that's negative 9i squared. So let's simplify this factor. We have x squared, then we have positive 3ix minus 3ix, so that's no x's. And then we have minus 9 times I squared. We'll always replace I squared with negative 1, right? That's the simplification there. And now we have our 1 times x squared minus 6x plus 9 times, this is x squared plus 9. I'll do one more distribution to simplify this completely. So the x squared has to multiply each of these. That's x to the 4th plus 9x squared. The negative 6x has to multiply each of these. That'll give us negative 6x cubed minus 54x. And the 9 has to multiply each of these. So that's plus 9x squared plus 81. Okay. Let's look along, see if we have any like terms to combine. And we'll get these in descending order. So I had x to the 4th, I had negative 6x cubed. I've got a positive 9x squared and another positive 9x squared. So that's plus 18x squared. We have negative 54x's, and we have plus 81 for our constant. Okay. So our final polynomial that fits all of these requirements is f of x equals x to the 4th minus 6x cubed plus 18x squared minus 54x plus 81. So we did our work again. If we are given zeros of a function, we can use those zeros to write factors, and we certainly can do any distribution necessary to reach our polynomial form of the function.